Hey, what's up, people? What's up? What's up? Thanks for joining again. Welcome to my live stream. And tonight I'm doing another coding challenge from Leetcode.com. I'm going to give it a couple more seconds and I'm going to get started. Hope y'all doing well. Hope y'all grinding at everything you're doing. I'm trying to do the same. So without further ado, I'm going to go ahead and get started. So tonight we're doing a problem from Leetcode.com called Invert Binary Tree. It's an easy problem, and the problem goes as such. Given the root of a binary tree, invert the tree and return its root. So this is the first binary tree problem I'm live streaming. So we're going to see how this goes. Hopefully I get through it all right. In this first example, it shows a tree here, and then it shows the inverted version of the tree. As you can see, in an inverted tree, the children are switched. A binary tree only has two children. That's why it's called binary tree. That's why it's called binary. And so here you can see the children are swapped. And then as you go down the next level, those children are swapped too, like 9 and 6, 1 and 3, 7 and 2. And so it just gives example of a tree. And this is kind of like the array representation of this tree. You have to kind of know how that works. Well, you don't have to know how it works to solve the problem, but you have to know how it works to do a new input. And then example 2, you just basically see the 3 and the 1 are swapped. In example 3, if there's no root or children, then basically you just get the same thing back. And then there's some constraints down here. Number of nodes in the tree can be 0 up to 100. It's important constraints to know. If you're in an interview setting, you might have to ask about these, especially the 0 one, because you might write code that doesn't work for that. So you need to be aware of that, as well as the node value. I guess the node value really doesn't matter in this problem. I don't see how it does, because you don't even care about the value of the node. You just basically care about swapping the children for a given node. So let's jump into it. So how would I solve this? How I like to solve or start with all problems like this is basically to think through the problem in my head. How would I solve it with pen and paper? How would I solve it in my mind? And then try to apply how I would solve it to code, utilizing data structures and algorithms that I'm familiar with from my studies or research or professional experience in the past. So when I'm looking at this problem, it seems pretty simple on the onset, but like doing it in code, of course, is always tougher. But I basically just, at every level here, I'm just switching the left and right children of whatever node I'm on. So I just swap these children. So if there's a reference to the left one, there's a reference to the right one, I need to swap their values. And then I need to go to the next one, go down a level to 2 and do the same thing with 2, swap. But I'd be like over here, these would be switched, and I'd be swapping 1 and 3, which is swapped over here. And then I would need to go down to 7 and do the same thing with 7. So when I'm thinking about that, how would I do that? So first, I need to traverse the tree in code. I need to be able to start from you're given the root of the binary tree. So you're going to be given this 4 in this case. And in this case down here, you're going to be given a 1. So I need to be able to traverse the tree from the root from 4. So I need to be able to go to 2, then go to 1, then go to 3, from 4 to 7 to 6 to 9. And a way to do that is using like a depth first search or a breadth first search in code. So that's something you may want to look up on how to do. But you basically take the root, and there's a reference to the left and right children. And after you process the root, you want to actually recursively, or if you're doing breadth first search, you're not recursively doing it, but you basically want to move on to the children and then process the children next. And then so on and so on, process the left and right children of 2. So I want to have 4. I want to process it. Basically, my processing, what is processing in this problem? Inverting the tree, swapping the left and right children. So for 4, I want to swap the children value, the left. I want to make the left leg equal to the right leg, and I want to make the right leg equal to the left leg. And then I want to go to 2. I want to do the same. I want to process 2's children. Left leg needs to be equal to the right leg needs to be equal to the left leg. And then I want to go to 1. Does 1 have any children? No, so I stop there. And then so on and so on. So how should I do this in code? I'm going to jump over here to the code side, and hopefully this makes better sense when I start jumping into this. So on Leetcode, they give you, and in any problem you do this with, you're going to have like an object of what your tree node looks like. This looks different in different languages, but in JavaScript and on Leetcode specifically, this is what a tree node looks like. A tree node has a value. So for the 4 node, the value is 4. And then it has a left and a right reference. And what these left and right references equal to, it points to the left and the right node. So each node has a value 4 for this one, and a left and right like parameter that points to whatever next node is in its left or right children. What's its left and right children? In a binary tree, you only have at most 2 children. You don't have to have 2 children, but at most you have 2 children. So that's why this object is made with just the left and the right. If there was more children, it may be like an array of children. But since it's a binary tree, we know we only have left and right. So knowing that, if I can start this problem kind of knowing that this is how my object looks like. This is what root looks like. So I have a reference to 4 to begin with that's being inputted in my sample function that I need to fill out. So this root should have value that's equal, and this is not the code I'm writing, but I'm just showing this. Like the value should be equal to 4, and the left should be equal to that's not right, but equal to another tree node that has a value of, it was 7. And then its left and right are going to have another tree node that have a value of whatever the left and right of that one is. So just to explain like how this object works and how you can translate the visual representation of the tree to a code representation of a tree. And it's kind of with recursion and with dealing with trees, sometimes it's hard. It's one of the harder things to understand when you're first getting started solving problems like this, because it does become a little abstract. So having a visual of it and understanding the objects and the references is very important. So I'm going to start the problem to not use up too much time. And so when I start this problem, I know I need to take the root, and I basically need to check the root's children or whatever node I'm on and invert it. So I want to do this recursively, and this may be hard to explain, but I basically want to make a new function that I can call recursively. And recursively means that I'm going to call this same function inside of itself with a different input. So it's basically going to be like recursively calling itself like if you ever seen that movie Inception, where like the dude was in a dream inside a dream inside a dream and all of that stuff. That's kind of what recursion is. You're calling the same function inside of it to do inside of itself to do some sort of work. And that's something that you have to practice to understand. It's hard to wrap your mind around it at first, but once you get it, it kind of makes it easier. So I'm going to make a new function called, what do I want to call this function? I think I want to say like invert children. So I want to invert the children of the current tree, of the current node that I'm on. I'm going to call the items I'm on node, since root is the root, but root is not necessarily just every single node. It's the actual top of the tree that I'm in. So I basically, and then what they say in the problem is to return its root when I change the tree. So what I can do just proactively is just go ahead and return my root. But what I'm gonna do here is I'm gonna call invert children and pass in root as my first node. So I'm calling these nodes and I'm gonna pass this in as my first node. And you're gonna see soon the reason why I'm doing it like this. So let's see. Invert children. So the way to do recursive functions to me and traverse a tree is to think about the work you need to do at each node and not try to think too much about the recursion that's going on. You have to think about it, but not try to like destroy your thought process thinking about, oh, what's, I'm inside of this loop, inside of this loop, inside of, not loop, but inside of this function, inside of this function. Like, just try to think of what if you, when you're at any particular node, what do you need to do? So let's say I'm at node 7 and I just got into this function with node equal, and where node value equals 7. Well, what if 7, let me see. Yeah, so what happens if I'm in there with node equals 7? So at node equals 7, I need to swap its children 9 and 6. Or sorry, I'm over here. 7, I need to swap its children. Yeah, 6 and 9, but I need to swap them to be 9 and 6. So in that case, node left, I have node left and node right. What do I need to do with these? So basically in this case, I need to take node, I basically need to make node left equal to node right. And I need to make node right equal to node left. And I'm doing this wrong on purpose. Some of you guys might catch this. The problem with this is once I set node right equal to node left, now node left equals node right. And so both of these would just be node right. So what I have to do is actually keep a reference to node right, which I'm going to call it node. Oh, I'm just going to call it right node. That makes more sense to me. So I need to keep a reference, a local reference to node right. So then when I set node rights, which I can just do it like, let me see. I can say, so yeah, I need to keep a reference to node right. And then once I have it in a reference, I can update it safely. So now I've updated node right to node left. And then now I can take my reference and update node left with the right node. This might not make sense, but I have to do that because I can't swap these values without having another thing to hold the place, because once you swap one of the values, you lose it. So you have to keep it somewhere temporarily. You have to keep right somewhere temporarily so that I can set it to left later. Otherwise, I lose reference to it. And then after that, what do I need to do? So as we talked about in the start of the problem, I need to jump to the next node, left and right. I need to also process those next. So I need to do this invert children again on node right and node left. So this is where the recursion comes in. I can just call invert children on node right or node left. I'm going to go node left first, and I'm going to go node right. And this is what's called, I might screw this up. I think it's in order traversal, or no, pre-order traversal. It's one of them. I actually forgot that. So somebody check me if you know the traversal types, in order, post order, and pre-order traversal. I can't remember which one it is, but I'm not actually looking at the value first, but I am processing this node first, and then I'm moving on to the left, and then I'm moving on to the right. So once I go into left, I'm always going down the left chain first before I move to the right chain. And that's something you have to kind of like practice, understand. So one thing I missed here is the edge case, which maybe I should have just like went through and made a mistake just for like a teaching moment. But what happens when I get to 9 and I'm looking at 9's children? 9 doesn't have any children, but I still call. So what happens when node left or node right is null, and I come back into my recursive function? Well, node, this is going to blow up. This is going to cause an unhandled exception because node doesn't exist. It's undefined and it doesn't have a right because it's completely null. So I need to have a check here for if node equals to if node is null or undefined, I can just say, I think I can just do that. If like node is undefined, then I just want to return null. I just want to basically just break out of my recursion. So this would basically make sure I stop. At some point, you need to stop your recursion. So whenever you're doing recursion, there always needs to be a like a stopping point. Like what stops it, and what stops it here is when left or right equals null, and it will always eventually equal null because it's not an infinite tree. This tree eventually ends at some point. So let's see. Yeah, so I have left and right. And this looks about done, I think. Yes, I return null here. Yeah, this looks about done. So in Leetcode, you can just run this and see what the solution is. But in the interview setting, they may not allow you to run the code. They may just want you to write it and talk through it. And they want you to review the code. In that case, in any case, you need to review your code and make sure it makes sense manually first before you run it. And if you can't run it, then you need to actually trace through this manually. And also, if you're in school, and doing tests, like when I was in school, maybe it's different now. When I was in school, we wrote code with pen and paper, and so you couldn't even like run it, which was, I thought it was weird at the time, but now looking back on it in retrospect, man, it's just like this. Like it kind of was representation of what you actually do in like an interview sometimes. And it just helps you learn. So anyway, I'm going to run through my code kind of mentally. I have invert tree was my main function that I was given I need to fill out. I'm going to call invert children with my root. My root is comes in here, and then if it's null, I'm going to return null, so that gets me out of my recursion. Here, I'm going to set right node, so I keep a reference to right node. I'm going to set left equal to right. I don't care about right anymore because I care about it, but I can mutate it without worrying about losing its value because I set it here. And then I can use that reference to set left node. And then I go recursively into left node and right node and process those. I'll come back into this function with this one, and I'll do the same thing on that one. So I'm like kind of dynamically or recursively traversing this tree to process and swap every single node's children, if that makes sense. So another thing that I like to do, and that you might have to do, especially in an interview setting, is like run through an example of a tree or some code manually before you try to run it. So I'm gonna do like 4, 7. So I'm just making like a tree here. And this is one of the tricks I've seen that I start doing, where I actually like make a little virtual representation of the tree here. And I'm gonna start with a simple tree for the sake of time. I'll make this one 6. So my root is 4, and then I'm gonna make like I want to make like a whole nother version of this tree that I can like swap so we can see the differences. So my root is 4. 4 is going to come into a node with value 4 and left and right pointers to 7 and 6 is going to come into this function. And I'm going to call invert children on that. And his null is node null. Like this null, if it is, I need to return null. No, it's not, it's 4. And so I'm going to set right node equal to 7. Oh, sorry, I'm going to set right node equal to 6. So I actually need to keep like, I put all my variables here. So right node is equal to 6. I'm going to set right node equal to left node. So, oops, I meant to do that on this one. So now they're both equal. This is why I had to keep a reference to right node. So now I have right node, sorry, is equal to, wait, hold on. Left node, right node. Yeah, I'm setting right node, so my bad. This is wrong. This is supposed to be 7. And I kept right node at 6. And so now when I set left equal to right node, I have the reference to it here. And I can set it to 6. And so then I come into this. I start calling recursively. I send left node down. I send right node down. These are both null because I'm at the end of my... Oh, no, I'm sorry. They're not null. These will actually come into here. So I'm going to send 6 in first because I'm calling left node. And then when 6 comes in, is it null? No. And then I'm going to swap its children. Since it has no children, these are all null. So I won't even like do anything for these. And then I'm going to pass in left node and right node. But these are null now because I'm on 6. And so when these come in here, it's going to say if not null, but it is null. So I'm going to return null and in my input. So based on this running through it manually, I see that this works. And so I think from here, I'm just going to run it just to like not take too long on this problem. And so Leetcode allows you to run these. And I got an accepted state for my first test case. So I expected, it's hard to read this in this format, but it's basically this example 1. And what Leetcode allows you to do is take, I think Leetcode just updated actually. So I think I can just like change the test case. Yeah, I can just like click this. I used to have to like type these in manually yesterday. Like now today they updated so I can just click to the next test case and run it. Oh no, it didn't. Oh, it did run. So I just have to click to the next one here. That's cool. So yeah, I passed every test case. I used to have to do this manually. So yeah, that works. And then you can submit it to Leetcode to see kind of what your overall score is against the rest of the Leetcode users. And this is a new screen to me. They just redid all this. So it doesn't even say, dang, it doesn't say anymore. Oh no, it says it over here. See, I'm sorry, I'm confused. This is brand new today. So I beat 27% in runtime, and I beat 87% in memory. And that's the one thing I forgot to explain. I usually don't forget that, but is the runtime complexity and the space complexity. So big O notation for the complexity of the algorithm itself. And for tree problems, a lot of times, because you have to traverse the tree, it's usually you're gonna have to check every node. So it's usually gonna be big O of like n, where n is like the number of the nodes. In this case, I'm not doing any like complex work to go to do any like thing that would cause me to have to look at a node twice or look at a node an exponential amount of times. I'm just looking at a node one time. Here, I'm not using any space. I'm not using any data structures besides for the tree itself. I'm not like storing anything additional to the input. So the space complexity is linear or big O of 1. So time complexity big O of n because I'm looking at every single node. And then space complexity is linear big O of 1 because I'm not using any space besides for the constant space of doing the problem, like setting these variables. It's nothing, there's nothing as far as variables I'm using that is tied to the size of my input. So that would that if the scale of my input went up extremely high would change the space complexity of this problem. So hope that makes sense. I appreciate you guys watching. Saw one of my professors from school was watching from Facebook. Thanks for joining. I'm surprised you even remember me. This was like 10 years ago. He said, I'm proud of you. Like, I appreciate that so much. My cousin's on here. Appreciate it, man, for joining. He streams too. Blackie Chan on Twitch, he streams too. So shout out to him. I appreciate everybody for joining. Please let me know if like any problem you want me to do, or if things don't make sense, or if you have any suggestions. Ram, my friend, jumped on here. Keep coming on live coding. Thank you. I'm gonna keep going. Guys, let me know if like anything that you want me to do in the future. Please, whatever channel you're watching this on, like, subscribe, share the video. That helps me do more content like this and keep going with this. And yeah, I'll see you guys in the next one.